So yesterday the question was how much additional how much additional reactant should be used to completely consume the limiting reactant? So we need to add a little bit more HCl. So I would start off with a more precise number. So this would be like calculation number 4, like we did yesterday, an add-on calculation. And so if we want to figure out how much extra HCl will be 0.1650 grams of magnesium that is left unreacted. And so what we do is we go from grams of magnesium to moles of magnesium. From moles of magnesium, we go to moles of HCl, pure HCl. And then from moles of HCl, we'll go to grams of pure HCl. And then from grams of pure HCl, we'll go to grams of HCl solution. That's what we're going to do, just the stoichiometry amount. Basically, all these conversion factors is your usual. This one's going to be different. This one's going to be 100 grams of HCl solution for every 50 grams of pure HCl. That's the conversion factor we'd use to do that additional step. So this would be it. If I had asked you that, but I didn't ask you that, those particular questions. Okay, then there was one other question, and then I'll get to that one. What was the other question somebody had?
Number 32.
32.
That would be true, right? Because when you have acidic, you're going to have an excess of protons. So then you'd want the most electronegative, so you get the electrons, because the hole would be the strongest, right?
Yeah. Basically, acidic hydrogens are going to have the most positive charge on it.
So it wants the most negative.
Yeah. Right.
Okay.
That's true. 32 is true.
How about?
And then, the other question was about the gases. But before I do the gases, let's take a look at the resonance form. Did you write down the 3 resonance structures for carbonate that I drew on the board?
Yeah.
If you wrote those down, then what we try to do is we try to average it. When we average it, this is what we come up with. There's a single bond on each of the oxygens, always. And the double bond floats between the 3 oxygens. How do we show it floating between the 3 oxygens? Actually, it doesn't float, it's just smeared out. This is like water. We just dash it. That's just showing it's what we call delocalized. And then there are 2 lone pairs on each oxygen permanently. And then the 3rd lone pair is smeared out over it. In 2 of the structures, basically we have a total of minus what? Minus 2 over how many atoms? Over 3 atoms. So if you have minus 2 over 3 atoms, that means minus 2/3. And these bonds here are what we call 1 and 1/3 bonds. 1/3 bond.
Why is it minus 2/3 and not minus 1/3?
Because you have a total charge. What's the total negative charge? Negative 2 divided by how many oxygens? 3.
Is the negative charge minus 1?
It's a minus 1, but you have 2 of them. So 2 minus 1 charges gives you a total of
Why do you
minus.
have 2 of them? Why do you
Did you write down the structure? Did you copy the structure? Did I not circle 2 negatives on the oxygens? Why do you have?
This is for HCO3 minus, right?
No, I'm doing carbonate since I didn't want to write the structure down for carbonate.
Oh.
This is carbonate here,
Yeah.
not HCl3 minus. I'm just doing carbonate. Otherwise, I didn't want to rewrite all the structures.
CO3 minus. Okay, that makes sense.
So how about number 50?
All right, well, let me do this really quick here before I get there. This stoichiometry problem we could do by gases too. Shoot, I shouldn't have erased it here, but basically we could make this into chapter 14 stoichiometry. The way we can make this into chapter 14 is I ask you how many liters of hydrogen are produced. And so there I'd have to give you the pressure and the temperature, and you'd have to calculate the molar volume and then just tack that on. And so we could split it off here. So for example, if we go grams of magnesium to moles of magnesium is solid, then to moles of hydrogen. Hydrogen is a gas. And then from moles of hydrogen, we could go straight into liters of hydrogen gas if we have the molar volume. The molar volume. The molar volume is just the nRT over, what was it? RT over P. That was the molar volume. Do you guys recall that? Yeah. 1 molar volume is particularly useful, 24.45 liters per mole. I wonder what temperature and pressure was 24.45 liters per mole, molar volume. Not STP. 1 ATM and what's the temperature? 25 degrees C. And so if this were 1 ATM and 25 degrees C, then I'd just use 24.45 liters per mole. This is 1 ATM and 25 degrees C. And then I could just go straight from moles to liters. That would be like an example of gas stoichiometry problem. But there are other problems. And since you know what, last semester I got behind, and that meant cramming some stuff at the end. This semester I'm through chapter 14, so I want to conclude chapter 14. And so what I did was I forgot to post this. If you look at Piazza now, there's a sample exam number 4. Let's just take a quick look at the sample exam number 4 and see what kinds of questions might be asked for gases. Sorry, this is late. Since this is late, we'll go through it together if you want. All right, question 1. Calculate the number of moles of nitrogen in a 10-liter sample at 19 degrees C in 1 atmosphere.
Is there any chance we could have the weekend to go over this and like take our time with this practice test so we could be more prepared for chapter 14?
Well, the practice test, what are we doing now? We're going through the practice test the day before the test. How many people actually went through this over the weekend?
Yeah, because it was like 1 week ago.
Actually, how many people have done the chapter 14 homework?
We did it.
You did it? Did you guys not want, one of the complaints I got last semester was cramming too much stuff at the end. If you're okay with that, then I'll move it.
Or could we just include chapter 14 but take the test on Tuesday?
Just chapter 14 test?
No, like all of it. Like have the weekend.
Oh no, we can't do that because the next test is in 3 weeks.
That's right. But like what if tomorrow we covered what we would miss next week and then we take the test middle of the week next week so we have time to...
I can, you know what, the easy thing, I'll just eliminate chapter 14 from this test. If I eliminate chapter 14, then we'll just put it on the next test. If this is, a shot. We'll do that. We can do that.
So we'll have 10 to 13 tomorrow?
Yeah, 10 through 13 tomorrow.
So I need homework from 10 to 13 to do tomorrow?
Yeah, turn it in.
And not 14?
Did you already finish 14?
No.
All right, then just 10 through 13.
Okay.
Let's do 10 through 13, chapters 10 through 13. So we're going to have 10, 11, 12, and 13 for tomorrow. We'll throw in, so it'll be like this. So they'll line up. Chapter 14 is a very short chapter. If you read through it, it's not as long as 15. 15 is so long, but 14 is bite size. It's fine. We could do it. The next test is fine. Then it'll line up. It's fine. We'll just do that. All right. What was the other question then?
15, number
39.
39.
Yeah.
CO2. CO2 is an example of a.
No,
This is the last one.
Oh, this is. $39.
yeah.
Somebody want to draw it? Shima? Shima had a perfect one. So if you draw it just like hers, you'll be fine. That's good. That's how you want to draw it.
Professor, what if we don't have a long term?
If you don't have a lone pair, let's say it's trigonal planar.
Trigonal plane. So like no, we have
Oh,
another.
a bond,
Yeah, like another.
like ammonia,
Yeah.
ammonium. Then you know these two are in the plane. Ammonium would be like that.
Oh.
You know, I forgot we had Spartan on this computer. Show you. What about the EG? What's the EG on this? That's your hedral. What's the MG?
Trigonal pyramidal.
Yeah, trigonal pyramidal is what it looks like.
And the angle would be 1.95.
Yeah, the bond angle would be. This is a quantum mechanics program here. So this is I submitted this for calculation. This is ammonia.
So that would be 120.
No, the bond angles always measure from the shortest. The problem is this looks like 120, right?
Yeah.
But it isn't 120. You got to measure from the shortest. The shortest, like for example, what if I did that? Hey, that looks like 90 and 180. Is that 90 and 180?
No.
No, it's because you got to think in 3D. If you think in 3D, you look and you put these three in a plane. When you put these three in a plane, then the angle comes out to 109. 109.5.
It would be
109.5.
But we have two long, one long.
There is one lone pair on
So
this
it should be
one.
one.
It should be 107. In fact, let's see what the, let's go ahead and measure the angle.
So each extra electron is going to be.
About a 2 degree. That's a total guess though.
Okay.
It's a total guess, but what did Spartan predict the angle to be?
106.
106.36. So 106, 107, it's close enough. It's a guess, a guesstimate, you know. That's it. Okay. Other questions? Oh, there's one other thing on this one, and that's the electrostatic map. You see the red is portions of negative charge density or positive charge density? Negative charge. The blue is regions of positive, the green is about neutral. And so this just shows the distortion in the electron cloud, causing it to be polarized. Yeah, this is for polarity. Ammonia is a polar molecule. It's unusually polar, so we call it hydrogen bonding. It's unusually polar.
Can we go over 14 through 16?
well, since we'll come back to the multiple choice. Since that's smart enough, let me just do that really quick. So for example, if we want chains, I did the calculation takes a little bit of time. So this is chains here, right? This is glycine. We did glycine in class, if you recall. And so we take each atom one at a time. So what was this one here? What's the molecular geometry? Not trigonal planar. There's a lone pair here that we don't see. This is glycine. This is trigonal pyramidal. This carbon, tetrahedral. This carbon,
No, bent.
bent.
No, it's not bent.
It's not bent. Bent would be like water. This one, okay. This one is trigonal. Now look at it. Is that planar?
Yeah.
This is trigonal planar. This one. However, this nitrogen is not trigonal planar. Do you see? It's distorted. It's trigonal pyramidal. And so this carbon here is trigonal planar. This oxygen here is, okay, Lucienne, you can bend. This oxygen is bent here. And so we did glycine in class. Remember drawing this?
Yeah.
If you could draw glycine, you're doing pretty good with this. You do that. And this is what it looks like. Models really help. Models.
It's like a
Yeah. Little rhino. Okay, but what you see is sometimes you see the zigzag pattern of tetrahedral EPGs. Zigzag. This oxygen tetrahedral EPG, carbon. This is sp2, unfortunately, not tetrahedral, etc. Okay, what was it? 14 through 16. Was that right? 14 through 16?
Yeah.
All right. What did people get for 14? True or false? Microwaves are higher in energy than infrared. False. False. Memorization. 15. What?
Should be false.
14 should be easy to remember. What's up next to red?
Infrared.
What's next to violet?
Ultraviolet.
And then you know it's got to be lower in energy. Microwave, because microwaves. Continuous spectrum means energy is quantized.
It should be false.
That's false. It means it's continuous.
That was
16.
true.
A H lamp, a hydrogen lamp, produces line spectrum.
Yeah, because that's when the
No.
electrons go up to the high level and bounce back down, they emit the light.
Yeah, that's true.
That's true.
And 17 is true, right? Too,
Oh,
right?
hydrogen.
Modern day scientists visualize electrons occupying orbitals around the nucleus. That's true. Orbitals. Orbitals. What are orbits?
It's the path.
Are orbits and orbitals the same thing?
No.
Okay, good. All right, other questions?
Helium is smaller than hydrogen because hydrogen has fewer. Isn't it like the fewer electrons they have, the more pull towards the center?
Hydrogen.
No, that's not the way we explain it. Somebody else? Uh-huh.
Helium holds its electron closer. Valence electron closer.
Why? Yeah, that's exactly right. Why does it pull its electrons closer?
More
Because of the
protons.
Negative 2.
So that's
Okay,
why
Shima has the answer. Helium has 2 protons, hydrogen has one proton. So 2 protons is going to have twice the force, according to Coulomb's law, than 1 proton. And so it's like a tractor beam, it just pulls it in. It's invisible force, so it's electromagnetic force.
So because it has 2 protons and that force is going to attract it.
Yeah, right. The more protons, the stronger the pull. Yeah. You can clearly see this when you look at the orbitals. When you look at the orbitals shrink as you go, as you get more and more protons.
So,
There's a really good figure in the Chem 1A book.
but there was an exception. Didn't it say that sometimes the number of valence electrons makes it bigger?
Shells. If you add another shell of electrons, then it's going to get bigger.
So within the same row, the one with the most protons is going to be the biggest.
This is going to be the smallest.
Smaller. So so the trend goes up and to the right
For the smallest.
for the smallest. So helium
This is the smallest.
The smallest, and francium's the biggest.
Right. Exactly.
Professor, what did you mean by there are 2 possible values of S?
2 possible values of
S
S. What question was that?
24.
24. 2 possible values of S.
Yeah, because the bigger the atom, the
What about
more
samples?
space between the nucleus and the electrons, so the electrons are easier.
There are 2 possible values of S.
Yeah. There, how about them both?
What does it mean?
It's because there are 4 quantum numbers. What are the letters?
S,
S, L,
and L,
M,
S.
and S. And so I was talking about the quantum. I should have been more descriptive. I meant there are 2 possible values for the quantum number S.
So positive 1/2, negative.
Yes, right. That's so it wasn't that good of a question. The way it was written was ambiguous.
Which one was that?
24.
So that should be true.
That should be true. But some people were confused last semester. I remember this. And,
Because it could be S1 or S2.
they were thinking like 2s, 1s, 2s, 3s orbitals. The letter designation. There are two. The letter designation for the orbitals comes from sharp, principal, diffuse. But this is to make this better. I should have said there are 2 possible values of S, the spin quantum number. Plus 1/2 and minus 1/2. If the arrow's pointed up, you call it plus 1/2. If it's pointed down, you call it minus 1/2.
Professor, how many questions like number 3 will be in the test?
How many questions like number 3 will be on the test?
Yeah.
Number 3.
That's true.
Yeah, there are going to be questions like number 3. Maybe I wouldn't say more than 3, like number 3. But I might put in more or less because what are the rules you use? Yeah. What are the possible values for n? 1 through 7. So if I said an n of 50, is that allowed or forbidden? It's allowed. It's infinite, right? And so if I said an n equals infinity, is that allowed or forbidden? It's allowed. And so I could ask you one multiple choice question on n. I should ask you one multiple choice question on L. What are the possible values for L?
Infinite as long as one less than
Yeah, it has to be all values from 0 to a max of n minus 1. And so if I asked you, what are the possible L values when n is equal to 6, what are they? If n equals 6, what are all the possible L values? 0, 1, 2, 3, 4, 5. And all of those are valid. And then I could ask you, what are the possible m values?
Does n only have one value, or does it vary as well?
It could have one, but it varies.
So like if so let's say n is 1, so my L will be like from 0 to 2, or will it be like negative?
No. If n equals 1, this is the map we have. If n equals 1, then you only have one possible L value.
Yeah.
L equals 0.
Oh,
And therefore, we only have one possible m value.
which is 1. Maybe it's a 0.
No, which is 0, which means one orbital. We call this the 1s orbital.
And so,
But if n equals 2, then we have, this is the this is page 5 of the quantum handout, by the way, if you want to see it written like this. If n equals 2, then what are the two possible L values?
1.
L equals 0 is possible. If L equals 0, what's the possible m value?
0.
0. And this gives us our 2s orbital. But if L equals 1, that's also possible. If L equals 1, what are our possible m values? 0, yeah, -1, +1, so a total of 3. Those are my 3 2p orbitals. So it's split up differently in the supplement. The way I did it.
Is 4 true?
Yeah, I'll look at just a second. I'll look at 4, but here it is in the supplement.
Professor, what page is this?
This is page 5 in the supplement. This just maps out all the allowed values. If n is equal to 1, only one L value is allowed, 0. And with L equals 0, there's only one m value allowed. If L equals 2, there are two possible L values, 0 and 1. If we're at 0, then it's 0. And then these are the S values here. If it's a 1, then we have 3 possible, -1, 0, and +1, right? And then we go on. And so this is building up all the possible ones. However, this is going from the top down. When we build up the orbitals, we go from the bottom up, when we build up the diagram.
what page is that?
Page 5 of the quantum. This is called quantum 5. This is table 1. This just maps out all the allowed quantum numbers. And so I might ask you, is n equals 1.5 allowed or forbidden? Forbidden. So there are a bunch of questions I could ask, but I'll probably limit it to about 3 at the most.
So-
1 or 3.
So n is just any whole number from 0 to...
Yeah, right. It has to be an integer.
Okay.
Can we go over polarity as well? Because I know like if they're really far apart on the periodic table, then they're going to be more polar. But like for carbon and oxygen, they're pretty close together. So is that polar or?
It's polar, right. It's polar
Because well,
covalent.
What's an example that it wouldn't be polar? Except for like if you have carbon and carbon, that's obviously not polar. But like would carbon and nitrogen be polar or no?
I'll try and give you that.
The rule is, and it's just a gray area. Does somebody have the cutoffs memorized?
The what memory?
The cutoffs for delta En. Do you remember delta En, the difference in electronegativity? If the delta En is between 0 and about 0.5, what do we call the bond?
Oh yeah, and 0.5 to.
Okay, how about 0 to 0.5? What do we call 0 to 0.5?
Non-polar.
Non-polar. Zero 0.6 to
1.5 polar equivalent.
greater than 1.5.
Ionic.
ballpark.
So then how do you calculate the coefficient?
You're given the electronegativity.
But you're,
So you're gonna give us the electronegativities on the exam, you don't have to memorize it?
You don't have to memorize electronegativity, but you should know the pattern on the chart.
Oh.
This thing.
so then, for number 27, how would you know which bond is most polar? Would it just be the ones that are furthest apart?
Yeah.
So it would be hydrogen.
You don't need to do any calculation. I'm not asking you to calculate. I'm not asking you to categorize. I'm just asking you which one's the most polar.
Could be hydrogen 4.
Yeah.
That makes sense.
Okay, what else? All right, so I guess I had to burn through another day for review. We haven't started, so tomorrow, I mean, not tomorrow, but on Monday, we gotta go through well, maybe it's good, go through the chapters quickly and then just review. And so we'll do that for the remaining stuff. But I'm not gonna start anything new, so we'll just finish off reviewing stuff. Is there are there any other questions?
Can we just do number 12? That's true.
Number 12. For the metabolism of glucose, what mass of CO2 is produced when glucose is metabolized to produce 1,000 calories of energy?
That's 6,000.
So I guess we could map this out, or we could, just try to figure out based on dimensional analysis. Did anybody get this?
Yeah.
Number 12? What did you get?
392.
392B.
Yeah.
Anybody else get B? Yeah? Well, how did you do it? Tell me your strategy here.
1,000 calories of energy.
Okay, so
From glucose.
1,000 capital.
Yeah, and then
C.
1,000.
1,000 little calories per big calorie.
And then 4.24 joules per 1 calorie small. And then 1 mole of glucose would be 2.832 times 10 to the 6th.
Should it be negative or positive?
Negative.
Should it be negative or positive? It's got to be positive. It's got to be positive. We got to say released in this case. Rather than write the negative sign, we're going to write released. Yeah, otherwise, we're going to get negative grams.
Okay.
And, okay, and then what?
6 mole CO2 over 1 mole of glucose. And then 44.01 gram of CO2 over 1 mole of CO2.
Okay, and then you got 392 grams?
Yeah.
That's good. That's good.
That looks good.
Okay, other questions?
So then you go 44 gram CO2 per mole of CO2. Get grams of okay. The hardest part for me with these is like knowing what needs to be on top and bottom for.
You just gotta make sure it cancels out, you know, everything. If everything cancels out, then you're okay. It doesn't quite cancel out. I made a mistake. There should be one more conversion factor for me here.
Joules to kilojoules.
Yeah, right. Or kilojoules 1,000. Just gonna make sure it cancels out. Do you guys know how to draw tetrahedral structures?
I think so.
No?
That's chapter 13. Right?
Does somebody want to draw a tetrahedral? We'll take a look and see how. Tetrahedral structure?
Are they like this?
Like methane. You know, can somebody draw methane? That's all right. Let's see your methane. I want to compare.
I'm just like confused about
Okay. Yeah, that's fine. That would be fine. That would be 100%, right, Joe? That's how you would draw it. The reason you want to draw it like this one is because if I gave you a longer chain, so if I asked you to draw ethane, well, if you draw ethane, you just add a carbon here, and you just continue the chain. Well, if you want to continue the chain, then what we want to do is we want to do the zigzag. So what I'm going to do is I'm going to flip this one, so these two are in the plane. And so this will be the start of the zigzag. And then what we'll have is we'll have one H coming out, and then one H going in. We did this. This was the central carbon in glycine.
yeah.
And then if we continue this, we want this zigzag pattern. So I'm going to put two in the plane, and then that means one sticks out, one sticks in. And so this would be ethane, then propane, and then butane.
The second carbon can be like dash first and then.
Well, then we want to draw it so we can flatten it out in a zigzag pattern like this, so that we can just keep drawing the chain without having to circle around or
No, I
go
mean
down.
like the carbon, we have the wedge first and we have dash second. The second one is dash, the first one is wedge. Can it be like the first one is dash, the second one wedge?
No.
Because the dash is supposed to be the back and then the wedge is supposed to be the front.
Yeah.
The wedge should be.
The dash is supposed to be at the back, so
Yeah.
this is wedge, say we're flipping.
Oh yeah, right.
Are you saying it could be like this? That's possible if I drew the dash on this side like that, but it's got to go in the back. It can't come out. And so I could put it on the left side or the right side, depending on which way I want to twist it. You know, actually they're superimposed, so you can't really see it. Yeah. Yeah, it depends. If you look at it from this angle, then it would look more like this. If you look at it from this angle, one's gonna come out like this, and one's gonna go in like this. So you're looking at this angle. However, if you go to this side, then it looks weird. And so if you go to this side, it should be looking like this. Or you know, it depends on which side you are. Because you're just looking at, these are the legs of this, like this.
Oh, okay.
And so,
it depends on which side you look, from this side or from that side, you know, how you draw. Okay, uh-huh.
What would you recommend, as a general outline, the best way to approach this studying tonight? Do you think we should focus more on structures or polarity? Given what?
Polarity's not that big of a deal. I wouldn't focus too much on that. Structures are a big deal.
Okay.
So the three-dimensional structure is a big deal. And so you should know that. Drawing loose structures is a big deal. And, doing limiting reagent problems is a big deal. You should know that. And so you just look and then think, okay, what were the most important things that were discussed, and then focus on those, you know, for this coming chapter. Okay, well, you know, if there aren't that many, any other questions, we'll wrap things up then. Good luck tomorrow. If something comes up, just post it on Piazza. I'll try to look at it.
Wait, we have a seven tomorrow?
I'm sorry?
Oh. You said good luck, I thought you weren't gonna be here.
No, I'm going to be here. Yeah, or if there are questions, you can ask at the beginning of class tomorrow too.